All right, everyone. So we finished off everything we need to say about derivatives, and we now want to start doing a couple of talks about undoing derivatives. So kind of a brief introduction to undoing some of the things that we've done for the last 3 or so months, and then this is the main focus, or at least half of the focus of what you'll do when you go off to Calc 2. Okay, so the main idea is this. Whenever we have mathematical operations, we have ways of undoing them. So for example, we have addition, but then you can undo an addition with a subtraction. So for example, if you take some number, you add 3 to it, and you undo it by subtracting away 3, you get back what you started with. If you take some number and you multiply it by 3, you can undo that multiplication by dividing by 3. And then the same goes for exponentiation and logarithms. So we'd like to do the same thing for derivatives. So what we'll say is that some function capital F is an antiderivative for little f of x on some interval I if f prime of capital, or if the derivative of capital F is little f for every x in I. Now, there is one very important adjective in this definition, and it's this an. So why is it an instead of the? So for example, if you take some number x and you multiply it by 3, there's only one number that you're going to get when you divide back by 3. So why does this say and instead of the? Well, the reason is that you could always add a constant to whatever you came up with. So if you gave me some function, some capital F, so that its derivative was little f, I could take that capital F and add 17 to it, and whatever this new function is, when I take its derivative, will still give back little f. So you can actually get an infinite number of antiderivatives for a function. Okay, so for example, we'd like to find some antiderivatives for these various functions. So another way that you could think about what we're doing here is we're playing Jeopardy. So you're being told what the answer is and you're having to come up with the question effectively. So we're saying what function, when we take its derivative, gives us x squared, or square root of x, or 1 over x. Okay, so for example, what is a function capital F such that the derivative of capital F is x squared? Well, we could say what gives us something with an x squared in it when we take a derivative? X cubed gives us something with an x squared. But if we just took x cubed, we'd get 3x squared, which is 3 times what we want. So we'll just divide by 3, and we'll say, if we take capital F to be x cubed over 3, when we take that derivative, we get x squared. What about if we want square root of x? Well, we know from the power rule that we'd want something with a 3/2 in the exponent. And again, when we take care of the constants and things, we'd want to start with 2/3 x to the 3/2. And lastly, what do we want to start with to wind up with a derivative of 1 over x? Well, we need to start with natural logarithm. Right, so this kind of gives us an idea of what we'd like to do. So we had a power rule for doing derivatives. We also have a power rule for doing antiderivatives. So if you give me some real number that's not -1, the antiderivative of x to the p with respect to x is given by x to the p plus 1 divided by p plus 1, and then you have to include this plus c, or plus a constant. So that is taking care of the fact that you could take any, add any constant, and you've still got an antiderivative. So whenever you're doing these kind of antiderivatives, make sure you just include the plus c. Right, so the important notation. So this kind of elongated s symbol is saying you're finding an antiderivative. Then you have what is referred to as the integrand. So it's the thing you're trying to find the antiderivative of, in this case x to the p. And then this dx is just saying what variable you're finding this with respect to. For us in Calc 1 or also Calc 2, this isn't that big of a deal because there's only one variable in the expression. When you go off to Calc 3, you could have 2 or 3 or more variables, and then including the variable that you're finding the antiderivative with respect to becomes very important. For us, just it's a notational thing. Just remember to include the dx. It's good for notation, but also if you don't, it will cost you points. And then if you picked the number -1, your antiderivative of x to the p is the natural logarithm of absolute value of x, and then again, plus c. Okay, so let's think about the steps that we're doing here. So when we would do our power rule for derivatives, we would take the exponent from our expression, we would multiply it out in front, and then subtract 1 from the exponent. What we're doing here to come up with our power rule for antiderivatives is we're adding 1 to the exponent and then dividing by the new exponent. So we started with x to the p, we add 1 to that power and get p plus 1, we then divide by that new power. And what we're doing is we're reversing the two steps of the derivative power rule, but we're doing them in reverse order. So we're undoing the subtraction by 1 from the exponent first by adding 1 to the exponent, and then we are undoing the multiplication through division. Okay, and then we have a few more rules that will show up. So one is that if you take the derivative of a constant, you get 0. So if you integrate the value 0, it's just a constant. Again, this makes sense because what we're asking when trying to find this antiderivative is what function do we have to start with to give us 0? Well, just a constant. Constant multiple rule. We know from our rules for derivatives that we can pull constants out in front of derivatives. We can do the same thing with antiderivatives. We can pull constants out in front of functions. Not a big deal. Sums and differences, we know from our rules for derivatives, we can add and subtract functions when we take their derivatives. So the derivative of the sum is the sum of the two derivatives. The same thing applies for antiderivatives. So we can find the antiderivative of a sum by finding the sum of the two antiderivatives. So antiderivative of f plus antiderivative of g. And then a couple of rules with exponents. So we know that e to the x is its own derivative, so e to the x is also its own antiderivative. And again, plus c's for everything. For regular derivatives, we know that the derivative of e to the bx is b times e to the bx. So if we want to undo that, we do the same kind of thing. We get 1 over b times e to the bx for an antiderivative of e to the bx. And then there's this last one that probably will never show up, but I include it for completeness. Okay, and then there are also antiderivatives for trig functions. So the important ones that you would need to know are sine and cosine. The other 4, there's really not much you're going to do with them. You'll probably see them more in Calc 2, but the important ones for us are going to be these first 2. So the antiderivative of sine is minus cosine, and this is usually the one that throws people off. Again, you're asking what function do you have to start with to take a derivative and get sine? Well, we know that if we take a derivative of cosine, we get minus sine. So if we start with minus cosine and we take that derivative, we get positive sine. So the antiderivative of sine is minus cosine plus c. The antiderivative of cosine is sine plus c. So one example here. We want to find sine of x over cosine of x squared, and we have the dx there. Okay, so we're asking what function do we have to start with so that when we take its derivative, we get sine over cosine squared? Well, if we start with capital F of x as secant of x plus some constant, when we take that derivative, we get secant tangent, and secant is 1 over cosine, tangent is sine over cosine, so we'd get sine over cosine squared, which is exactly what we'd like. Okay, now there's this other, so we can also talk about one other application for antiderivatives, which are referred to as differential equations. So the idea is that you want to find some function y that's going to satisfy a couple of conditions. So for example, if you said, find me a y so that y prime is equal to x squared plus x, you'd want to say, well, if I start with y of x is x cubed over 3 plus x squared over 2 plus c, that is what we refer to as a general solution. The reason it is a general solution is because of that plus c. You could wind up with a whole family of different functions But then if we throw in an initial condition, so what we're saying is this function has to pass through some particular point, we can then use that to solve for the plus c. For example, so if we said we want to find the function y so that y prime is equal to x squared plus x and y of 0 equals 1, we can then say, the c must be equal to 1, and this function y equals x cubed over 3 plus x squared over 2 plus 1 is a particular solution. So we'll do a couple of examples of those. Okay, so the first one that we're going to do is we want to find y prime. We want to find a function y so that y prime is equal to 3 over t plus 6, and y of 1 goes through 8. So what we can do is find antiderivatives of these two pieces. So an antiderivative for 3t is 3 times natural logarithm of t. Really, we could have absolute values here, but we said that our value for t has to be positive, so we don't need to include the absolute values here. And then an antiderivative for 6 is 6t, and then we have our plus c. If you have multiple antiderivatives, you only need one plus c because we're saying it's an arbitrary constant that we're going to solve for later. You don't need to have a plus c for the first one and then another constant for the second one. One constant will do. Now we want to apply our initial condition. So we said that y of 1 is equal to this expression that we have here, 3 natural logarithm of 1 plus 6 times 1 plus c, and we said that's equal to 8, so solving for t we get 2, and this allows us to conclude that our particular solution is going to be y of t equal to 3 times natural logarithm of t plus 6t plus 2. So that function will have the property that y of 1 is equal to 8, and y prime of t is equal to 3 over t plus 6. Okay, so for the second example, so we'd like to find a position function so that the acceleration is equal to 4, the velocity at time 0 is equal to minus 3, and the position at time 0 is equal to 2. So the first thing we'll do is anti-differentiate the expression. So we have a is equal to 4. If we find the antiderivative, we're going to come up with a position function, or the velocity function, the first derivative of position, and that will be 4t plus an arbitrary constant c. We can then use the initial condition that v of 0 is equal to minus 3 to solve for the c. So we'll get 4 times 0 plus c equals minus 3. C has to be equal to minus 3. We'll then go and anti-differentiate again, so we'll take 4t minus 3, find the antiderivative of that, and we'll get 2 times t squared minus 3t plus k. The reason I use k here is because really this is a different constant than the one before, and I'd rather not use c to mean two different things. So we just need to solve for the value of k. So we'll use the second initial condition. We'll use that p of 0 equals 2. So we have 2 times 0 squared minus 3 times 0 plus k equals 2, and that tells us that k equals 2. So this tells us our particular solution is going to be p of t equal to 2t squared minus 3t plus 2. And that will have the property that the acceleration is equal to 4, the velocity at time 0 is equal to minus 3, and the position at time 0 is equal to 2. Okay, one last example. So the prior one, just some of the terminology that you would see in differential equations, this is what's referred to as an initial value problem. So you have initial conditions at the same point, so in this case times 0. Here this is what's referred to as a boundary value problem. So you have, in this case, two conditions on the position. Okay, so the first thing that we'll do, as before, is we will anti-differentiate once, and we'll again get 4t plus c. But now we don't have any initial conditions at all on the velocity, so the only thing we can do is take another antiderivative. And if we do that, we get a position function of 2t squared plus ct plus k. Now we have two unknowns in here, c and k. We also conveniently have two conditions that we can apply to solve for the c and the k. So we'll find that p of 0 is going to be 2 times 0 squared plus c times 0 plus k equals 2. That tells us k has to be equal to 2. And then we can apply the other initial condition to solve for c. So we know that p of 2 has to be equal to 4, so we'll say that 2 times 2 squared plus c times 2 plus 2 equals 4. And solving for c, that'll tell us that c has to be equal to minus 3. So putting in the expressions for c and k, we get a particular solution that is incidentally the same thing as before. P of t equals 2t squared minus 3t plus 2. Okay, so that gives us a worthwhile introduction to finding some antiderivatives and some of the things we can do with them. So the next videos that we'll do are going to talk about finding areas under curves, and then we're going to tie together some ideas with areas and antiderivatives. All right, so I will see you all then.